right, so this problem is really similar to a homework problem. I was just going to go over how you would work through this problem. This was the problem where you were making cuts, square cuts out of the corner of a paper and tossing out the corners. So you would kind of cut these corners out and throw them away, and then fold along those dotted lines to make yourself a 3D box. And they wanted the value of X that would give you the largest volume of that box. So let's kind of imagine what that box would look like in 3D. Okay, so if I draw a little side here, we're going to fold up and get something that would approximately look like that. Right? 3D box. Okay, and the height of this box, well, let's first think about, they want us to maximize the volume. Okay, so we want to maximize a volume function. And for a box like that, the volume is going to be length times width times height. And that height, which is right here, that comes from this little box up here in the top diagram. Okay, when I fold that up, that is just whatever that X value is that I choose to cut out of the box. Okay, the width of the box, so that distance, that pink distance down there, that's going to come from this distance, what's left of the short side of the box when I fold it up. Okay, well, the long side of the box was 3 meters, but then I cut out 1x here and 1x here. Okay, so that pink distance right there is just 3 meters, but it's missing 2 x's. Okay, so down here on the bottom, we'll label that 3 meters minus 2 times x. Okay, likewise, the length of my box, the long part, comes from the long part of the paper that's left. Okay, and that paper, that would be 6 meters minus 2 of these x's. Okay, so this is going to be 6 meters minus 2 x's in the corner. All right, so let's see. I've got my length, 6 minus 2x. I've got my width, 3 minus 2x. And my height, we said, was just the x. All right, so my volume function is 6 minus 2x times 3 minus 2x times x. Okay, so we always are trying to get our function, what we're trying to maximize or minimize, get it down to one variable, which we just did. We got it from length times width times height all the way down to just a bunch of x's. We want to pick a reasonable interval for x, okay, because we're going to find the absolute maximum on this interval. So you want to think, what are the lowest possible value that we could pick for x and the highest possible value we could pick for x? Okay, so the smallest possible value that I could pick for x, remember x is the size of this square, the side length of this square. Okay, so the smallest thing that I could do would be cut out nothing, okay, 0. I can't go any smaller than that. I can't cut a negative size square out of the corner. 0 will not make for a very good box, okay? It'll be a box with no height, all right, but that's still the smallest thing I could pick. The biggest value that I could pick for x, okay, remember that this side of the box right here, the short side of the box, is 3 meters long. So the biggest square I can possibly cut out is where I pick half of that. Okay, that also is going to make a pretty dumb box. All right, but that's the biggest thing that I could possibly pick for x. If I try to go to any bigger, I can't cut out 2 of them. So 1.5 is going to be the biggest possible value that I can get for x. All right, so I know that my solution has to be somewhere between 0 and 1.5. All right, so to find the absolute maximum of our v function over that interval, I'm going to have to FOIL out my v. I need to find critical points for that function. I need to take the derivative and set it equal to 0. So I'm going to FOIL this out. Let's start by FOILing out these 2 factors. All right, so first terms give me 18. My outer term, 6 times negative 2x My inner term's negative 2x times 3. And my last term's negative 2x times negative 2x. And then I've still got that x hanging out outside. And again, I'm just simplifying this because I need to take the derivative to find critical points, to find absolute maximum. Okay, so I've got 18 minus 18x plus 4x squared times x. And then I'm just going to distribute the x through. Okay, so there's my volume function. All right, so my maximum volume is either going to be at x equals 0, x equals 1.5, or at some critical value in between those two. So now we want to calculate our critical values. So let me go erase everything. We'll just recopy our volume formula. Okay, so I figured out that my volume formula was 18x minus 18x squared plus 4x cubed. And we wanted to find the maximum on the interval 0 to 1.5. Okay, so let's find our critical values. I'm going to take the derivative of my volume function. I get 18. Bring down the 2. That's negative 36x. And then take the derivative of 4x cubed. I get 12x squared. All right, so I need to find my critical values, which I get by setting this equal to 0 or figuring out where it's undefined. It's not going to be undefined anywhere, so I just need to set that equal to 0. So I'm going to rewrite that in descending order so it looks like a regular quadratic equation. I'm also going to factor a 6 out of everything because all three of those coefficients are divisible by 6. So factor out a 6 out of 12x squared. Factor a 6 out of negative 36x. And factor a 6 out of 18. Okay, so setting 6 equal to 0 doesn't do anything. Setting 2x squared minus 6x plus 3 is where we're going to find our solutions. Okay, so let's set that equal to 0 up top here. 2x squared minus 6x plus 3 equals 0. And that doesn't factor. I'm going to have to use the quadratic formula. So x equals negative b. For us, that's negative 6. B squared minus 4ac. All of that over 2 times a. All right, so those are our critical numbers. We're going to get 2. So we'll get 6 plus or minus square root 36 minus, let's see, 4 times 2 times 3 is 24. And I get a 4 down here. So 36 minus 24 is 12. All right, and I could just type that into my calculator, but square root of 12, I can simplify that. That's 12 is 4 times 3, so let's pull out the 4 out of the root. Square root of 4 is 2, and the 3 has to stay inside. All right, and you can see the 6 and the 2 and the 4, those are all divisible by 2. So I'm going to divide everybody by 2. 3 plus or minus root 3 over 2. All right. So those are my two critical numbers, 3 plus or minus root 3 over 2. Okay, so I'm going to go figure out what those numbers are. I've got x equals 3 plus or minus root 3 over 2. So just type those into your calculator to see what those are. Of course, on your exam, I got to make sure that these numbers are doable without a calculator, but that's my worry and not yours. Okay, so when I do 3 plus the square root of 3 over 2, I get 2.366. And then I'm going to do it all over again with a minus. 3 minus square root of 3 divided by 2. And I get 0.634. Okay, now remember that we are finding the absolute maximum of our volume function, which I already erased. Let's recopy that down here. And we decided that our reasonable interval was 0 to 1.5. Okay, 2.366 is out of that interval. If you think about x, the corner of this box being 2.366 something, that would be pretty big. And then when I went to go cut out the other corner, I would be overlapping. I'd be cutting in space, you know, like I can't cut that section out twice. Okay, so 2.366 does not make sense as a critical value. So 0.634 is our only answer. And now we just need to verify that that's actually going to give us the maximum volume. We just need to plug in our endpoints and our critical point. We only got one into the original function. Okay, so we're going to take 0, 0.634, and 1.5 and plug them into our original function. Okay, so this one we can do in our head. That's a whole lot of 0. Okay, so not cutting anything out of the corner gives you a volume of 0, a box of volume 0, which we already said we knew. Okay, so when I plug in 0.634, okay, I get 5.2. Let's see if I can squeeze that in there. There we go, 5.2. Okay, so that's a volume of 5.2 meters cubed. And then when I do the same thing for 1.5, that's cutting the whole entire 3 meter side off. This is going to give us nothing. It's also going to be a 0 volume. When we plug that into our calculator. All right. So that makes sense as well. Okay, so remember absolute max and min, you plug in your endpoints, you plug in your critical points. The biggest thing you see is your absolute max. So our absolute max happens when x is 0.634 meters. Okay, always units. I forgot to label these units in my diagram. Meters. All right. Okay, so that's your critical point. That's your answer to the problem. All right, so check in for another one. I'm going to do a different video here in a minute.